Welcome to BSTA 378. This is the third part of Chapter 9, and the topic today is Factorial Design. We have already learned about completely randomized design, we've learned about the block design, and today we will learn about Factorial Design. In this situation, we will have to consider two factors or explanatory variables. For example, suppose a company is doing an experiment with two-level prices and three types of advertising. One factor will be the price, and the second factor will be the type of advertising. What we have to consider now as a treatment will be the combination of price and advertising. We specify the price, we specify the advertising, and since there are two price levels and three levels of advertising, so it will be 2 times 3, 6. Therefore, we have here 6 treatments. This type of situation is called factorial design, when we can use all the possible combinations of each of the factors. We call that a complete factorial design. We will assume that all treatments have the same number of observations, although it is possible to do factorial design without equal sample size. We typically refer to ANOVA design by the number of factors and or the number of levels within a factor. What we learned in the one-way ANOVA, we refer to a design with one factor. The two-way ANOVA has two factors, like in this case, price and advertising. The three-way ANOVA will have three factors. Suppose we have price, advertising, and location of the store. Therefore, for example, a 2 by 3 ANOVA is a two-way ANOVA where the first factor has 2 levels and the second has 3 levels. A 3 by 4 by 2, therefore I will have a first factor with 3 levels, the next one has 4 levels, and the third factor with 2 levels. Therefore, factorial design allows us to determine if there are interactions also between independent variables or factors that are into consideration. If there is such a thing as an interaction between factors, then it means that one factor influences the other factor. Therefore, it will be very hard to study their individual contribution to the variable. Let us take a first example, the effect of brand and the shelf location on weekly coffee sales. In this example, we have two brands of coffee, brand A and brand B. We also have 3 shelves positions that we will consider here, at the bottom, at the middle, or at the top. There are a few questions that we'd like to ask ourselves. What are the answers to these questions? What are the experimental units? Each week is the experimental unit where we will collect information. What is the response Y? Well, the response Y will be the weekly coffee sales. For example, at week 1, we will collect information on the sales of coffee when it is brand A, position bottom. What are the factors that we are considering in this experiment? There are 2 factors, the brand of coffee and the 3 positions. What are the factor levels? Factor brand of coffee has two levels, brand A and brand B. And the other factor, which is the position, has three levels, bottom, middle, and top. What are the treatments? The treatments will be the combination of a type of a brand of coffee and the position. So basically there are 2 times 3, 6 treatments for each experimental unit. And for each cell we have 3 weeks of observation. The two-way ANOVA model can be represented this way. Y as a function of mu plus alpha I beta j plus alpha beta ij plus E the error. The first Y is the observation corresponding to the level I for factor A and level J for factor B. Mu is the overall mean. Alpha is the effect of factor A at that level. Beta J is the effect of factor B at level J. Alpha beta represent the interaction between the two factors. And E is the random disturbance like we had in regression. The hypothesis testing that we will do is the following. We will test for the effect of factor A and the effect of factor B. Those are called the main effect. And this is what we are mainly interested in. We want to know the sales at different position in the store or the brand of coffee, one of the two brands of coffee. But before we move there, we have to look at possible interaction. Interaction means that the effect of factor A may depend on the level of factor B. In our example, it could be that brand A of coffee sells much better when it is at the bottom of the shelf. If there is no interaction, the main effects are independent of each other. And this is the reason we need to start by testing interaction. If we have interaction, then the main effects will not be powerful. Conclusion. The degrees of freedom associated with the different components of our analysis of variance are easily understandable. Assume that my factor A has N1 level. Assume that my factor B has N2 level. In this example, it's 2 and 3. And suppose that we have R observation for each treatment. Think of R for repetition. The 4 sources of variation and their associated degrees of freedom. Factor A, since it has N1 level, it will have N1 minus 1 degree of freedom. Remember the regular ANOVA. It is the number of degrees of freedom associated with treatment. This was number of treatment minus 1. For factor B, since factor B has N2 level, it will be N2 minus 1 degrees of freedom. The interaction between the two, it will be N1 minus 1 multiplied by N1, N2 minus 1. The error, N1 times N2, N2 R minus 1. And the overall, for the total degrees of freedom, we remember it is always the total number of observations minus 1. How many do we have? We have N1 level for treatment A, N2 level for treatment B, and R observation in each cell. Therefore, it's R multiplied by N1 multiplied by N2 minus 1. All the above results can be represented in the two-way ANOVA. We have the sources, factor A, factor B, interaction between A and B, the error, and the total. The degrees of freedom that we just derived are put in this column here. To find the mean square A, it's simply SSA divided by the degrees of freedom. Mean square B, SSB divided by N2 minus 1. Similarly for MSAB and MSE. We now have to consider 3F function. First F is the ratio of mean square A divided by mean square error. The second one to test factor B, mean square B divided by mean square error again. The interaction, mean square AB divided by mean square error again, in order to test if we have any interaction. Let's go back to this example. Well, we have brands of coffee at the bottom, at the middle, and the top, and the two brands of coffee. The first thing we will do is to find the average in each cell. The average in each cell here, 4 plus 5 plus 6, the average is 5. 7 plus 8 plus 9, the average is 9. And so on. I put in red the averages for brand A, and in blue the averages for brand B. There is a visual method that will help us identify if we have possible interaction. I will first put at the bottom of the scale here bottom, middle, and top. So this is my factor B, B1, B2, B3. And on the left, this axis will represent the sales. For each one, I will represent here at the bottom, I start with brand A. The average is 5, so I'll put here 5. The average for middle and brand A, it will be 8. Here is 8, and it ends with the 7. I will do the same thing with the brand B, 10, 14, and 5. I notice that the two lines intersect. When the two lines intersect, it means there is a possible interaction. It does not tell me at 95% certainty, but it tells me there is a possible interaction. Now let's look at different models for interaction. If the two lines are almost parallel, there is no interaction. If the two lines are not parallel but do not cross, interaction does not appear to be serious. We can treat the model without interaction. In this model here, the line almost coincide, no interaction, and no A effect. And this example on the right, the lines are almost horizontal, no interaction, and no B effect. The graphics that we will get will never be as clear as this, but if the two lines cross, the segment will cross, we believe there is a possibility. Let us take a second example about printer sales. The company is experimenting with the price of its top-of-the-line printer and how it is advertised. They set the price at either $600 or $700, and the advertising was either by television, radio, or newspaper. They record the sales for the month, and each combination was run twice. So therefore we have 12 observations. If I was working with Excel, the data would be presented this way. Advertising 1, 2, and 3, price 1 and price 2, and this is the sales. To run this analysis in SAS, I need to create a column with all the sales, a column with the level of prices, and a column with the level of advertising. This is how SAS will do it. The first question we ask is there significant interaction between price and advertising? If there is a strong interaction, it might be hard to sort the effect of each factor. But if there is no interaction or it's not really strong, we test for main effect. Let us prepare the data to be ready for the analysis. Many of the calculations can be done manually, but we will also see how to do it with SAS. I start with the information that I have here. For each level, price 1, advertising 1, I have 18 and 16.8. The average is 17.4. The average between 12 and 13.2 is 12.6. 7.8 at 9, it's 8.4. Also, for each pair, I will also calculate the standard deviation. Therefore, I have this matrix. For the 3 level of advertising and the 2 prices, for each one I got the mean and the standard deviation. The first thing we will do is to see if we have possible interaction. As we did previously, I will put my 3 level, my factor B, advertising 1, advertising 2, advertising 3. For advertising 1, and the price is 1, I am all the way at 17.4. Advertising 2 at 12.6. Advertising 3 at 8.4. Similarly, I will do it for price 2, which start at 14, at 10.2, and at 9.1. I can see here there is potential interaction between the two levels between my 2 factors that we see because the 2 segments will cross. Would it make a difference if I put at the bottom here price and here at the level of the column here advertising? I will have similar results. Let us try to build our table. Now I need for each row, now that I have established I have a potential problem of interaction, I will continue and do the calculation and test it at 5% level of significance. Price 1, I will take the average of the means for price 1 and it gives me Y bar of price 1. Y bar A1 12.8. It's the average of the 3 means. Also for price 2, I will take the average for each group. I can do that because they all have the same number of observations. 14.35 plus 10.2 plus 9.1. It will give me an average of 11.217. This is my Y bar A1, Y bar A2. I will do the same thing for each level of the factor B. The average between 17.4 and 14.35, it gives me my Y bar B1, my Y bar B2, Y bar B3. At this point, I did not use the standard deviation, but it will be useful in the calculation of everything else. I also have derived here Y bar bar. It's called the grand mean. It's the average of these Y A1 bar and Y bar A2, and which is equal to the average of Y bar B1, Y bar B2, and Y bar B3. Suppose I take the average of those YAs, and it's not the same as YB. It means I made a mistake. Therefore, my Y bar bar, or my grand mean, is 12.01. I still need to calculate SSA, SSB, SSAB, SSE, and SST. We have the formula for each one of them. Let's take the easy one. SSA, it will be take each Y bar AI minus the grand mean, square it, times the number of observations, and 2 times R. This is, I think, for SSA, the difference between this Y bar A1 minus 12.01 squared plus Y bar A2 minus the Y bar bar squared multiplied by the number of observations, that was used to calculate these averages. 3 levels times in each group, each cell, I had 2 repetitions. Similarly for SSB, N1, R1, the sum of y bar bi minus y bar bar square. SSE will be the sum of the individual standard deviation in the cell square. Standard deviation here is 0.8485 square plus 0.8485 square, 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 and square. That will give me times the number of repetition minus 1. This is my SSE. SST, the sum of square total, will be obtained by taking the variance of all the raw observations I had at the beginning times big N minus 1, where big N correspond to R, N1, and 2. It's more difficult to calculate the SSEB or SS interaction, but I know that the total of everything is my SS total. Let's see how we did that. Therefore, we follow the procedure 12.8 minus 12.01 square, 11.217 minus 12.1 square, multiplied by number of observation 2 by 3. Similarly for SSB and SSE. And the total. Of course I need that. This is the standard deviation of the total. I need to have calculated that. I need to run it by SAS and I'll have my answer. Therefore, to calculate the SS for the interaction is the total minus SSA minus SSB minus SSE, and it will give me my SSAB. I now have everything to put my results within the table, and I have the following. We've just calculated the degrees of freedom corresponding to price 1 is the number of level minus 1, 2 minus 1. Price B, advertising B, number of level minus 1, 3 minus 1, 2. For AB, 2 minus 1 times 3 minus 1, which is 2. And we continue like that. And the total, we know it's the total number of observation, 2 by 3 by R, which is 12 minus 1. So all these observations can be obtained. Because I have my summer square, my degrees of freedom, I find my mean square. Mean square A, mean square B, mean square AB, and mean square error. And I can find the corresponding F value. Therefore, the first thing we will do is to test for interaction at 5%. This is my level, so we will have H0 no interaction, H1 interaction. We will reject H0 if F is my F that I have here is greater than an F. Where will I get the degrees of freedom? Degrees of freedom for interaction is a 2 and a 6. That's why it's 26.05, which is 5.1433. I will compare this value here. 5.87 that I found here is greater than 5.1433. Therefore, there is a possible interaction. I've rejected H0 possible interaction. There is at 5%. But if I do my calculation at 0.01, and there's 26.01 is 10.9248. My F from the table now is less than this. I could conclude no interaction. I am between two values. Therefore, my p-value should be between 0.01 and 0.05. For the sake of the argument and presentation of the results, I will continue and I will consider this interaction not very serious. I can now test the main effect. If my interaction was very serious, very strong rejection, then I would not be able, I should not continue. But in this case, I will continue because my interaction feels more like borderline. Let us test now if there is an E effect. To test if there is a factor E effect, my hypothesis is let us test that the mean of A1 is equal to mean of A2. So that is the mean. The effect that we have here, the two prices, are they significantly different. I will reject A0 if F that I have in my table is greater than F1, 6. Where do we get this? I go degrees of freedom corresponding to price A is 1 and the error 6. 16.05, which is 5.897. This 10.99 is greater than 5.897. I reject H0, therefore there is a factor effect. So the price is different according to, well, the sales are different according to the price. Let's see now for a B effect, a factor B. The type of publicity. Does the type of publicity have an impact? Therefore, I'm testing is mu B1 equal mu B2 equal mu B3 against at least one mu BI is different. I will reject H0 if this F in my table is greater than an F2, because I'm looking at factor B, 2, 6.05, which is 5.1433. This F calculated in the table is greater than 5.1433. Therefore, we reject H0. There is a factor B effect. At least one BI is different. Always, we read the degrees of freedom from the table. Once we've established this, we don't need to go back to formula. Let us calculate a confidence interval. A 95% confidence interval for the difference in treatment means for $700 in television advertising and $700 in radio advertising. So let us see. I want to find this mean based on the Y bar of 700 TV minus Y bar 700 radio, plus or minus a T. And 1 and 2 are minus 1. If we recall, these are always the degrees of freedom corresponding to the error. Alpha over 2, square root of mean square error, square root of 2 over R, where R stands for replications. This was the table with the means. I want to have 700 in TV, which is right here, 14.34. The other one, 700 in radio, 10.2. So we have 14.34 minus 10.2 plus or minus a T, 23 times 2 minus 1, 0.05 divided by 2, mean square error, which is 0.684, square root of 2 over 2 repetition. The T that I'm looking for is 2.4469. Therefore, I have, in my calculation, it's 4.15 plus or minus 2.0263, and therefore the mean, the confidence interval for the differences in mean is between 2.12 and 6.17. Since 0 is not included in the interval, I can conclude, yes, the sales are different for the same price but different, those two different advertising. If I need only one pair, one comparison, it's no problem. This is sufficient. But if I need more comparison, then I am forced to use a family of intervals. I am forced to use either the Bonferroni or the Tukey. So let us find that. Let us see what we have. This is the pair that I have used if I only want to find a confidence interval for a pair of treatment. But the different, now my question is, I saw that the advertising are different. The means are not all equal. But which one is different? In order to look at this Bonferroni, I will need to derive the equation. Let's go back and see which equation would be required for that. On this slide here, we have all the interval that we need. First, I can find a confidence interval, for example, for 600 and radio. It's a simple interval of one cell. This is how we would find it. Confidence interval, for example, of TV and 700, I just substitute. If we saw for a pair, if I just want one interval, this is how we'll do it. Now for Tukey, suppose that we want to find the Tukey, the confidence interval, then I will have to use these formulas here. For each treatment, treatment A, pairs of treatment B, or pairs of treatment B. Q alpha is found in the table in the book like we've done in the previous lecture. For the Bonferroni, I'll have the similar interval, but I'll have to divide by alpha by 2G. So let us take Tukey. Let us use a family of Tukey to identify the differences between the types of advertising. So let us do that first. The first thing we will do is identify which formula we will use. I will use an interval for mu B1 minus mu B2 as, so this is the average of the sale y bar B1, y bar B2, plus or minus Q of N2, N1, N2, R minus 1, square root of mean square error times the square root over Rn minus 1. The first thing to find is what is this Q. From the table in the book, a Q 0.0536 is 4.34. Everything else is substitution only, where my Q correspond to 434, mean square error 0.684, R, number of repetition is 2, and number of factors that are involved with A, 2. This will give me this interval. Therefore, the mean B1 minus the mean B2 is between 2.68 and 6.27. 0 is not in the interval, then we conclude that the mean of B1 is not equal to the mean of B2. And we are 95% confident. Let's do that for B1 and B3. Similarly, I substitute in the interval. I still have the same Q value here. And we find this interval that does not include 0. Therefore, mu B1 is not equal to mu B3. And the last one we need to do, mu B2 and mu B3. We construct the interval, and we find from 0.855 to 4.44, again, mu B2 is not equal to mu B3. So what is my conclusion? All the three means are significantly different. My decision is valid at the 5% level of significance. I'm 95% confident of those conclusions. Let us see how SAS-EG gives us the information. SAS-EG has a very special way of presenting the two-way ANOVA. It's going to give me the sum of square SSA, SSB, and SSAB merged together. The degrees of freedom, 1, 2, and 2, merged together as 5, and the mean square. Therefore, it will give me an overall test for my equality of means. This one is this, and then SAS is going to expand this one into the 3 rows. This is how it looks. Now you can follow the video produced on YouTube on how to run a two-way ANOVA. This is how it will look with SAS. First, SAS will put in the model here 5 degrees of freedom. It has included all the sum of square of A, sum of square of B, and sum of square of AB. It would take the sum of square divided by degree of freedom, and it will give me an F value, and it says, yes, there is a significant difference. As usually, SAS is going to give us a table with the R square, coefficient variation, root mean square, and mean sale, that's the Y bar. And then it will take the model here, that row, and it will expand it as the price, advertising, and price times advertising, which is our interaction. Quickly looking at the p-value, I find, as we found before, that there is a slight interaction. The p-value is less than 0.05. I can reject, but it's more than 0.01. These are the results that we will find using our SAS EG. So let us remember that SAS will give us a table combining everything, and then the second table, the model, will give us the sources one at a time. This 119.304 is the sum of these three as we saw before. If I want to find the differences now, I will use this Tukey procedure. And now if I want to find the price, the difference, is there a difference between prices? Well, we had only two values and we've already decided that it was significantly different. SAS is taking a price comparison between 1 and 2 and 1. And it shows that 0 is not included, and the triple star shows that there is a significant difference. You will note that the critical value of the student price range is the value that we found in the table. The means with the same letter are not significantly different. I can see that the first price is associated with letter A. The second price is associated with letter B. Since they are associated to different letters, then they are significantly different. If my price were assigned the same letter, if they were assigned the same letter, that means they would not be significantly different. Let's just look at now for advertising. In terms of advertising, we have three different types of advertising. I could quickly look at the distribution of sales and advertising. That's interesting. We see this. Really, they are different from one to the other, but it is not with a level of certainty. If I look here, the means, the Tukey grouping, the mean advertising 1, advertising 2, advertising 3 correspond to 3 different letters. If they are 3 different letters, that means they are significantly different. Again, SAS is going to take the difference of mean 1 minus mean 2, gives me an interval, and with triple stars telling me that they're all significantly different. Therefore, everything is significantly different. All this corresponds because 0 is not there, then A and B will not be, advertising 1, advertising 2, will not be in the same box. Additional thing would be given in SAS. Now SAS likes to draw it, give us additional graphics for price times advertising, so that means for the interaction. What correspond to 1.1 is price 1 and advertising 1. Price 1, advertising 1, we have it here. Price 1, advertising 1, we have 17.4, which is here. It's a small box plot corresponding to this. The next one, 1, 2, level price 1 and 2, 12.6, so we go down 12.6. 1 and 3, 8.4, we are down here. And the same thing is done for all the region, all the level. That is giving us, if we merge them, it's telling me what happened when I put the price and the advertising together. Let us take a third example. Let's see how to analyze this situation. So we want to know how the number of hours of television people watch per week depend on gender and age. So first of all, what is this design that we will need? This is a 2 by 3. 2 gender, 3 age category. It is a 2 by 3 complete factorial design. Complete, it's because there will be observations in all the categories. Same number of observations. In each group, to understand what is given here, I have males between the age of 18 and 24, 5 of them. Here another 5. So this is a balanced design because I have the same number of observations in each cell. We go back again to calculate SSA, SSB, SSAB, SSE, and SST. But before that, I want to look at the possible, also I could look at the possible interaction. 2 by 3, complete factorial design. So let's do our calculation. For each one here, these are, I need the means. This corresponds to Y bar A1, y bar A2, y B1, y bar B1, y bar B2, y bar B3. And I start my calculation. 27.67 minus the grand mean, which is 31.1 square, plus 34.53 minus 31.1 square, times the number of observations that we used to calculate these means. It was 3 categories. In each category, I have 5 observations. 3 by 5. It gives me 353. Similarly for B, SSB1, I find 15.12. 1520. The total SSE here is the sum of the variance square, but now be careful. Here I have the mean and the variance. So the variance 14.4 is already the variance. I don't need to square it. If we don't read this carefully, we are probably going to make some mistake. Let us look at the plot to see if we have any interaction. They average for group 1, so my factor B is my group 1 here, age 1, age 2, age 3. So when I have age 1, so where are male at age 1? So I go male age 1, it is at 23.4. Male at age 2, 24.6, and then 35, since we have in red. And now in blue for female, female age 1, 26.8, 29.6, and 47.2. I have 2 lines that are almost parallel, and that they have not interacted, they are not crossing each other. So there's no intersection. That means no obvious interaction. Now I can build the table. From the previous slide, I have my SSA, SSB, SST, SSE, and the interaction again is the total minus SSA minus SSB minus SSE. It gives me 110. I have my full table. I calculate my mean square and the corresponding F value. Let us now test at 5% whether we have interaction. Again, no interaction against interaction. We reject H0 if F is greater than the F value from the table. Let's look at this again. We have to look at this carefully. I'm looking at the interaction. So the degrees of freedom for interaction is 2 and the error 24. This is why it is an F224.05. It's 3.4. I will reject if this F that I have in the table 3.036 is less than 3.4. It is less. There's no interaction. Now at 5%, I know I have no interaction. This is good. And then I go and change and test for gender. Again, gender, the degrees of freedom for factor A correspond to 1 and error 24. 124 and the 19 is greater. Gender is significant. Age, similarly, I find the age is significant. Both factors have an influence, have different number of hours of TV. They are different, but also they have no interaction. Now we saw that the age, the gender show a significant difference. I don't need to do any more tests because I have only 2 gender. The other one is the factor age. I have 3 age groups. I know they're not all equal, at least one is different, but which one? So let us use Tukey family to be able to identify them. We build a family, and I will need this Q value 3.5317 that I found in the table. We follow again similar, the same formula we had before, and we find from -2 to 4.7229, which is from -6.7 to 2.7. What does it mean? That means mu1 and mu2 are not significantly different because 0 is in the interval. Let's do it for mu B1 minus mu B3. I find from minus 20 to minus 11. 0 is not in the interval, then the two means are different. Again, for now B2 and B3, 0 is not in the interval, that means mu B2 and mu B3 are different. From what I have here, B3 is different from B1, B3 is different from B2, but B1 and B2 are not significantly different. Not all the means were significantly different. How it is done in Tukey, how it is done with SAS, you will find that the same intervals that we have calculated, look at here, H1 minus H2, minus 6.7 to 2.7. This is minus 6.7 to 2.7. The same interval we find using Tukey family of intervals. The minimum significant difference that is given here, 4.7229, look at it is the same quantity we have here, 4.7229, 4.7229, and 4.7229. We have everything. 3.53 is the student value found in the table. SAS identify with these stars which pairs are different. For H1 and H2, they are different. H2 and H3, they are different. But H1 and H2, since it doesn't have any star, they are not significantly different. If I was interested in only one pair, I did not care, I did not worry about the overall, but I'm looking only at one pair. Is the average hours of TV for male from age 18 to 24, is it the same as for female from age 25 to 54? Two pairs. So I will go get the average for male 17 to 24, that's their average. The average for female 25 to 54 minus 29.6. We also minus the t-value. Square root of my mean square error found in the table, 2 over r. I have in this example for 5 replication. I find here from minus 11.72 to minus 0.0679. What does it mean? It means that the two means are significantly different, and female from age 25 to 54 watch more TV than male age 18 to 24. This example is also found in SAS, where I will have here one column for gender, one column for age, and the number of hours. As we said previously, SAS will put together everything into one column and one row, and then it will spread the row and show us the individual results. If I quickly look at the probability at the intersection, I find its p-value is 0.0649. I cannot reject the hypothesis of no interaction. I can see from here too that the p-value shows that there is a difference according to gender, and there is a difference according to age. Similarly, I can combine female age 1, female age 2, female age 3, and combine them with male age 1, male age 2, and male age 3. To give us a little bit more visualization of the problems. The least square means, this is again adjustment for Tukey. It will give you something similar with the degrees of freedom, the confidence interval for female and for male, and the same thing, the degrees of freedom, the estimation for the mean for the two groups. This matrix here is important. This matrix here gives me something that we can work from. It's telling me that it is testing for me. Is the mean of one equal to the mean of the other one. When I'm looking here at age, if I look at these are the p-value. If I read this one here, 0.5489, this was tested if the mean of age 1 equal to mean of age 2, and I have here a p-value more than 0.05, it means they are not significantly different. If I look at this corresponding cell here, mean, the difference with mean of age 1 and mean of age 3, I find a p-value that is below 0.001. In this case, this is an indication that they are significantly different. Between age 2 and age 3, again, a p-value that will tell me this is very small again. Therefore, the confidence interval will be given to us also, so all the confidence interval that we need will be obtained in this one here. This least square mean value is another way to analyze the results. That's another way of analyzing the results for each age and the comparison between the age and the groups. Significantly different, and here significantly different in this one, not significantly different. A last example that will be presented here, and it will be for you to do in more detail, is a manufacturer whose daily supply of raw materials is variable and limited can use the material to produce two different products in various proportions. The profit per unit of raw material obtained by producing each of the two products depends on the length of the product's manufacturing run and hence on the amount of raw material assigned to it. The manufacturer has conducted an experiment to investigate the effect of the level of supply of raw material and the ratio of its assignment R to the two-product manufacturing line on the profit Y per unit of raw material. The ultimate goal will be to choose the best ratio to match each day's supply of raw material. We have three levels of supply of raw material. It's either 15 tons, 18 tons, or 21 tons. We also have three levels for the ratio allocation to the new product line. Is it a ratio 1 to 2, 1 to 1, or 2 to 1? We are asked to use a complete factorial design, and three replications are done. This is how the situation looks like. B, the raw material supply, and here the raw material, the ratios of allocation. There are a few questions that need to be answered. Do the data provide sufficient evidence to indicate an interaction between the groups? Let us look at the results from SAS. The first thing I am testing, is there an interaction? I can go right there and stable and find that if H0 is no interaction, H1 is interaction, I will be able to reject the hypothesis because this p-value is so small. Yes, in this case there is a very significant interaction. If I look at the individual, yes, there is the p-value is less than 0.05 for supply. There is a significant difference. And for ratio, not significant. But since we have a strong interaction, it will be very hard to evaluate these things separately. So we saw we have the interaction, we tested it, I find the mean in each category, I find the average of each one. This is the mean for 15 and 1.2, 18 and 1.2, and so on. And I have the following graph for B1, B2, and B3. What I can do at this time, since I have a very strong interaction between my variable, I will have to look at them differently and analyze them differently. I will be able to say a few things though. Not everything is impossible, but there are a few information that I can give for this one. I can say in the case of 15 tons, what would be the best ratio? If we look at the 15 tons, the profit is the highest when I use the ratio 1 to 2. In the case of 18 tons, I look at the best ratio. It would be if I use E2 1 to 1. In the case of B3 with 21 tons, I find that it is the best one is if I use A3, which is 2 to 1. The overall maximum profit is obtained when I use 18 tons and a ratio of 1 to 1. We can see that although we have interaction, we can still look at this picture and make some recommendation on the best approach. I can take one interval at a time without using Tukey or Bonferroni. So find a 95% confidence interval to estimate the mean profit per unit of raw materials when I use 18 tons and the ratio is 1 to 1. We saw over there that it was the best profit. Let's find that confidence interval. The average for that cell is 23.67, a T80. Always remember that the degrees of freedom for T correspond to the error. Square root means square error over the square root of R. I find an interval. The profit when I go for 1.1 ratio at 18 tons is between 21.79 and 25.55. The profit is superior with this approach. If I want to find the interval, the difference between the profit with 18 ton and R of 1,2 and 18 ton and R of 1,1, we'll see how big is this difference. We follow the previous formula and we find this interval from -6 to -6.68. And again, it confirms that the highest profit is found when I have chosen the ratio of 1.1 with 18 tons. The last comment I would like to make here is on the case of unbalanced factorial design. With the unbalanced factorial design, we see a situation like that when I don't have the same number of observations per cell. But when I analyze it in SAS, I still have my 4 values for A1, only 3 values for A2. I will be able to analyze it and to make also some conclusion. SAS will work with what I give, and I will still identify that I have here no interaction, factor and a factor A interaction, and a not interaction, a factor A impact, and no significant impact for factor B. This is a little overview of what is two-way ANOVA, factorial design, and I hope that you understood the approach, the experiment behind the scene, and that you enjoyed this special class that I am sending you from Jerusalem. See you soon in class. Thank you.